All right, welcome back. So, last time we talked about molar mass, which sometimes they call an atomic mass, or which sometimes will be referred to as a formula mass if you're talking about a chemical formula, or a molecular mass if the chemical is a molecule, right? And what it is the mass necessary to get a mole of whatever it is. It's an atom, the atomic mass, and that's what these numbers here are on the bottom of these of the periodic table. All right, so just a quick little review on that. We find the molar mass of something like water, right? And we can refer to that as the molar mass. You can always refer to it as the molar mass. We could also call it the molecular mass. And the molecular mass, again, is how much mass you need to get 1 mole of it. And oxygen is 16 plus the 2 hydrogens, right? So it's 17, 18. And do you remember the units on that 18?
Grams.
Per what?
Equals 1 mole.
That's right. 18 grams of water is how much you need if you want 1 mole of water. Okay, very good. We're going to also introduce a new concept called percent composition. Percent composition. And when we talk about percent composition, it's always in terms of mass. So, for example, if we want to know what percent of this compound, do you remember the name of this compound? What's the name of that compound right there?
Sodium. Oh, carbonate.
Very good. Sodium carbonate. We get out our list of polyatomic ions and we find the carbonate ion on there. Where is it at? There it is. Carbonate. Very good. Sodium carbonate. All right, so we can ask questions like, what percent of the sodium carbonate is made of sodium? What percent is made of sodium? Now, percent composition is always mass. Somebody might be tempted to say, oh, what percent is sodium? Well, there's 2 of the sodium ions for every 1 carbonate, right? You might think of it that way and say, oh, it's 33% because, or it's 2/3, so it's 66%. Or you might say, but that's not right. You might say something like, oh, there's 2 sodiums, 1 carbon, and 3 oxygens. Therefore, it's 2 out of 1, 2, 3, 4, 5, 6. It's 33%. But that's not how we do it either. All right? When we're talking about percent composition, you have to know what mass is contributed by the sodium. So we say, what's the molar mass of sodium carbonate? First, we have to find that. Can you help us find the molar mass of sodium carbonate? You want to do it on your screen?
Sure. What are we trying to figure out again?
The molar mass of sodium carbonate. Molar mass, which is how many grams you need of sodium carbonate to get 1 mole. So why don't you write the chemical formula for sodium carbonate there? Na2CO3 CO3. Very good. Now, how many grams of sodium carbonate do I need to get 1 mole? How do we do that?
Oh, wait. All of it together, not just sodium?
All of it together. 23, that's the mass of sodium, right? I have the periodic table here too. Good job. 23, there's two 23s. Carbon, I have it here so I can help you. It's, okay, that's 46. Good. That's a good way to do it. Do the sodiums. Carbon is 12. And oxygen is 16. 16 times 3 is 48. Very good. So 48 plus 12 equals 60. Okay, good. 60 plus the 46, is that 106? Okay, good. Excellent. So what are the units on that 106? Grams for every what? Mole, M-O-L? Very good. Grams per mole. 106 grams per mole. Very good. Now, to find the percentage of sodium in sodium carbonate, we just look at the mass that's from the sodium, which is the 46, right? That's how much mass the sodium contributed to the molar mass, the 46. You see that?
Uh-huh.
So then you take that 46 and you divide it by the 106. All right, take the 46 and divide it by the 106. And that will give you no, other way around. So it's 46 or 106 into 46. But do you have your calculator with you?
Yeah.
Just put 46 divided by 106.
Point 433.
Okay, very good. Now, if you multiply that by 100, that will turn into a percentage. Okay?
43.3.
Very good. Excellent. So let's go back to the other screen now. And we see that sodium, like you did the calculations, is 43.4% of the sodium carbonate. Okay, so what about the carbon? What percentage of sodium carbonate is carbon? How would we do that?
12 divided by 106.
That's right, 12 divided by the 106. And then times what?
100.
That's right. So what'd you get?
11.3.
Very good. 11.3%. That's percentage of carbon. Now, we could do the same thing with oxygen, the 48 divided by the 106. We could also, just know that the sum of all three of these is 100%, and I could do 100 minus the 43.38, and then subtract the 11.3, 100 minus the 43.38, and then subtract the 11.33, and what's left over, 45.29, should be the percentage of oxygen. Or we could also have just taken the 16 times 3, which is the 46, and then divided that by the 106, and then times by 100, and it should give me the same percentage, right? Whoops, did I do that right?
No.
What did I do wrong?
45.28, or if you have the percentages, 2.9.
Maybe the 106 isn't exact. Well, it's okay. It's close enough. We see that those two are essentially should be the same because it adds up to 100%. Okay, the sum of the percentages always adds up to 100 for all the different elements. All right, can you find out what percent of carbon dioxide is carbon? What percent is the percentage of carbon in carbon dioxide? Can you find that out for us? Why don't we go to your slides and watch you do that? What percent is carbon dioxide?
It is 12.
12 is carbon, good. Oxygen, 16. 16 times 2 is 32.
Find the percentage. So,
If you hold it flat, we can see 2.
12 divided by. Oh, wait. Second.
44, is that what it is?
Yeah.
Okay.
12 divided by 44 equals that, and then times 100. So it's 27 point.
Very good. Excellent job. So you 27.29%. Good job. Fabulous. All right. Now here's another way that a question might be asked, and we can still think about percent composition, even though it's not, we don't know the chemical formula necessarily, well, even though it's not presented the same way as before. So this question says, a sample was analyzed and it was found to contain 0.1417 grams of nitrogen and 0.4045 grams of oxygen. What's the percent composition of the nitrogen and of the oxygen in this compound? Now this time we're not given the, although we know the chemical formula is, well, we don't know if it's NO2 or N2O or N2O2 or anything like that, but we know it just contains nitrogen and oxygen. But we can still find the percentage by taking the mass of one of the elements and dividing it by the sum of the whole mass. Does that make sense? Did you understand that? Are you there?
Yeah.
Did you understand what I said or not quite?
Not quite.
Okay, so let me try to say it again. I can also find the percentage of my elements. So in this case, we're interested in nitrogen and oxygen because there's this sample here. Here's the sample. It contains just nitrogen and just oxygen. It has 0.1417 grams of nitrogen, 0.4045 grams of oxygen. All right. The total mass of this material that I have here is the sum of those two. So if I want to know what percentage of this material is nitrogen, I can just take the mass of the nitrogen and divide it by the total mass, which is the sum of the two. Did you understand that time?
So you have both of them, you separate them, then you divide it by the all of it combined, and then it equals how much is in 1?
That's right. So if I take, I'll do the nitrogen and you can do the oxygen. If I want to know what percentage the nitrogen is, I put the 0.17 grams of nitrogen over the grams total, which is the 0.1417 plus the 0.4045. And then if I multiply that by 100, that will give me the percentage of nitrogen in the total. Does that make sense?
Oh, yes.
Okay. So 0.1417 plus 0.4045 is 0.5462. And I'll write that down here. And then on top here, 0.1417, that's grams of nitrogen, and this is grams total. Then I can take the 0.1417 divided by 0.5462, 25, or then I have to multiply by 100, right? If it's not multiplied by 100, if you just look at the 0.25, that's not the percentage, that's called the fraction. The fraction, right? It's just this divided by that. So what fraction out of 1 is nitrogen? But if I multiply by 100, then that gives me out of 100 parts of this material, how many parts will be nitrogen? Okay? Very good. Now, do you want to do the oxygen?
Sure.
How are you going to find the oxygen? Because there's kind of two ways now that you could find the oxygen.
So now I do, how much is the oxygen?
It's 0.4045. 0.4045. That's how many grams of oxygen.
Divided by?
And the grams total was 0.5462. So just put a line underneath it to do divided by. There you go. 0.5462. So get rid of that 5 in the front. It's just 0.5462. Very good. Excellent. That's right. Grams of oxygen over grams total. So go ahead and lay your calculator down there so we can watch you work on it. Is it on?
0.44. .05.
Very good. Very good. Excellent job. Okay. That is an example of using mass percent. Finding the percentage. Okay, I have another problem here for you. This is another one. There we go. a 35.5 gram sample is analyzed and found to contain 23.5% silicon. What is the mass of silicon present in the sample? All right, so 35.5 grams of a sample. So here's my sample, right? It contains 35.5 grams. That's how many grams are in the sample. If it was 100% silicon, then how many grams of silicon would it be?
35.5 grams.
That's right. So if it was 100%, then what you would do is you would just take the 35.5 times the 100, and then you'd have to divide that by 100, and that would equal your percentage. In this case, it's 35.5 of silicon, the percentage of silicon. Okay. Another way to do it would be to take the 35.5 and multiply it not by the percentage, but the fraction. The fraction is always the percentage divided by 100. So 100 divided by 100 would just be 1. And then again, you would get the 35.5. So it's not 100% though in this case, is it? It's 25%. So what should I do instead? What should I multiply 35.5 by?
100.
No, because it's not 100%. This is what you would do if it was 100%. So you take the mass of the sample, multiply it by the percentage, and divide by 100, and then you get the percentage of your material. Right?
Oh, you divide it by 100.
You divide it by 100. What if it was, let's do a different example here, okay? Here's a pile of a different material. And this material is made up of X and Y. All right? And we'll say 50% of it is X. 50% of it is X. And the mass of this material is 20 grams. 20 grams. And I want to know how many grams of X are in this material. All right? 50% is X, and there's 20 grams of material. How many grams are from the X?
10.
10. That's right. So how can I get that with math? Well, I can take my grams of sample, 20, times it by 50, and then divide by 100. Right? That's 20 times 50 is 1,000. Divided by 100, that gives me 10. That would give me how many grams. Oh, this is not supposed to be percent. That's supposed to be grams of silicon down here. That was not supposed to be percent. So that's grams, 10 grams of my X. Another way to do it would be to, again, take the mass, 20, but now just multiply it by the 50 that I've divided by the 100 already, which is 0.5. And that would be, again, 10 grams of X. So you take the mass and you multiply it by the fraction, or you multiply it by the percentage if you're going to divide by 100. Okay? You don't need to divide by 100 if you take the fraction. What's that?
Can I tell you how I did it?
Sure, what'd you do?
Since 50 is half, you do half of 20 and then 10.
That's great. That's great. But the problem is with that, when somebody asks you, for example, 23.5% silicon, I don't have a number that's in my head already for 35.5 grams of material. I don't know in my head what 23.5% of 35.5 grams is. Do you have any idea how to do that one now? How would you do that with math? 35.5 grams sample, 23.5%.
$23. 20,
I can't hear you very well.
35 divided by 100.
35.5?
And divided by 1.
Talking to the microphone.
Divided by 100 equals 0.355. And then times it by,
Times the 23.5?
yeah,
Okay. What do you get?
23.5.
Wait, you did 35.5 times 23.5 divided by 100?
Oh. No, I didn't. 23.5 times 35.5 equals that divided by 100. 8.34.
Very good. 8.34 grams of silicon. Excellent job. All right. So you can either multiply the mass by the percentage and then divide by 100, or you could just take the percentage, divide it by 100 first, which makes it the fraction, and then you multiply the mass by the fraction. Okay? Very good. So, next slide. Now we're going to introduce to you two terms. One is called the empirical formula, and really that's the only new term because the other formula, term is called the molecular formula, which you're already familiar with, right? The molecular formula for a compound, I mean, you would only call it the molecular formula if it was a molecule, right? And you wanted to know that molecule's formula, then you could call it the molecular formula. All right. An example of a molecular formula is this formula here, C6H12O6. That compound is glucose, which is an important sugar in the diet of anything that lives, basically. All right. Everything needs to live off sugar. Well, I mean, everything that doesn't live off photosynthesis. But even that material, even plants that undergo photosynthesis are undergoing photosynthesis to make this sugar to consume themselves, right? So we all live off of sugars. We all need sugars. So the molecular formula for a compound is called the molecular formula because it is the formula for the molecule, and oftentimes the molecular formula can be simplified into what we call the empirical formula. Empirical. So look at this chemical formula, C6H12O6, and you can see that it can be simplified down to CH2O, where each of these values, the 6, the 12, and the 6, are all divided by 6. And then it is simplified down to CH2O. Do you see that? Does that make sense?
Yeah.
Okay. So this one, the C6H12O6, is called the molecular formula because that is what the actual chemical has in it. It has 6 carbons, 12 hydrogens, and 6 oxygens. But you can express its empirical formula as just 1 carbon for every 2 hydrogens for every 1 oxygen. Now, nobody would express the empirical formula that way. I mean, you would always express it in terms of its molecular formula. However, if you had a pile of the material, so here is some material, and I don't know what it is, and I'm trying to find out what it is, as the chemist would do different experiments to find out, he would find out, or they would find out first that the chemical ratio of the elements is C, 1 carbon, 2 hydrogens, and 1 oxygen. They wouldn't know that the chemical formula was C6H12O6 right away. They would just know that this is the simplest ratio. And that simplest ratio we call the empirical formula. Can you say empirical formula?
Empirical formula.
Very good. Empirical formula. And that's compared to the molecular formula. So next time, we're going to talk about ways that we can find the empirical formula for a compound simply by having information about the mass percentages of the different elements in the compound. All right. Thank you very much. See you later.